Hi guys, today we're going to talk about the derivatives of the 6 trig functions. But before I get to their derivatives, let's go over what the 6 trig functions are, and let's talk about their definitions. Now just as a reminder, a trig function is the ratio of the sides of a right triangle compared to an angle. So in my right triangle here, I'm going to talk about the angle x. And the first trig function I'm going to discuss is the sine function. The sine function represents the ratio of the opposite side of that angle, so if here's my x, go all the way across to its opposite side, divided by the hypotenuse, the longest side of a triangle. Now if I want to compare some of the other sides, say this one next to the x, that would be the adjacent side over the hypotenuse, and that's our cosine function. The next one is the tangent function, which is the opposite side divided by the adjacent function. And these are our 3 basic trig functions, and you can remember them with the acronym SOHCAHTOA. Now, don't forget you learned in pre-calc that you can write tangent another way. You can write tangent in terms of sine and cosine. Tangent is the sine divided by the cosine. Again, please keep that in mind as we're working through our problems in this section. Now, I can also flip all 6 of these trig functions over. So if I flip over the sine, I get what's called the cosecant function. Flip over the cosine, and you get the secant. Flip over the tangent, and you get the cotangent. Now don't forget, since tangent is also sine over cosine, cotangent is cosine divided by sine. The last 3 you have here, numbers 4, 5, and 6, those are all called the reciprocal trig functions. Now again, please keep all of these in mind as we work through our problems. Now all 6 of these trig functions have a formula for their derivative. Remember that derivatives come from the limit definition of a derivative. Here's some important limits you need to remember. The first limit is the limit as x approaches 0 of the sine of x over x, and that's equivalent to 1. You should already have a note card for that one. Another special limit we'll need in this section is the limit as x goes to 0 of the cosine of x minus 1 over x is equal to 0. So make sure you make a note card out of that one also. Now, like I said a few minutes ago, all 6 of the trig functions have a derivative, and they each have a derivative that's kind of on the easy side. But how did we get those formulas for the derivatives? How do I know what the derivative of sine is by using its formula? Well, what I'm going to do now is fade out and show you how I do this by solving it on the board in class. I'm going to show you how I take the derivative of the sine function using the limit definition of the derivative. So that would be f prime equals the limit as h goes to 0 of f of x plus h minus f of x all over h. And I'm going to apply that definition to finding the derivative of the sine function. So that would mean the derivative of sine is equal to the limit as h goes to 0 of sine of x plus h minus the sine of x all over h. And remember, that's me taking x plus h and plugging it in for that x and then subtracting off the original function. Now be very, very careful here. You have to evaluate this limit. You may not distribute trig functions over addition. There's a formula for that, and you should know it from pre-calc. So I'm going to go ahead and replace this sine of x plus h with this definition. And again, it is from pre-calc. It was on your summer assignment too. So I expect that you know it, and if you don't, look it up. It should be in the back cover of your textbook. So the sine of something plus something else turns into the sine of x cosine of h plus the sine of h cosine of x. And again, everything that I wrote right here is simply replacing the first quantity. I still have this minus sign of x on the end, and this is all over h. And now we need to simplify this. Some of the things I'm about to do right now you may not have thought of before, so make sure you take note of them, put them in your toolbox. And we're going to go ahead and rearrange this to try to get this down to one simple answer. And here's some of the things I see. I've got a sine x here and a sine x here, so I want to group those two together. So on my next line, I'm going to have the limit as h goes to 0 of sine of x cosine of h minus sine of x. All I did was take that thing that's underlined at the end and move it to the middle. And then this term right here, the plus sine h cosine of x, I'm going to write at the end. And this is all over h. Now this h on the bottom you are allowed to give to every single term in the numerator. So if I just give it to these two, I'll deal with them separately. But if I give this h to this term, I'll have sine of h over h, which is the same as sine of x over x. So I'm going to go ahead and split this up. I'm going to write it over here. Limit, as h goes to 0, sine of x, cosine of h, minus the sine of x. And that's all going to be over its own h. Completely legal. And then I'm going to add to it this second term off to the side. That'll be sine of h, cosine of x, all over h. And I think now it's a little bit clearer for you to see that there's the sine of h over h. And that's going to go to 1. So 1 times the cosine is going to be the cosine. Now this term, let's revisit that sine of x and sine of x. Since they're common, I'm going to pull them out as a GCF. So I'll have the limit as h goes to 0, sine of x times cosine of h minus 1. That's what happens when you pull that sine of x out, all over h. And then don't forget I have plus the result from this term, just the cosine. And I think now that I've pulled out that sine of x, you can see this quantity right here, cosine of h minus 1 over h, is the same as this thing you made a note card out of. And that goes to 0, which completely cancels this first term. So the limit then is just of this cosine. And since the variable is h, cosine of x is your answer. So what I've done is I've taken the derivative of sine and reduced all of the limit definition stuff down to just cosine when you take its derivative. Now I know that was really quick. However, you can rewatch the video as many times as you'd like to see how I went ahead and factored everything. Now I can repeat this process to get the derivatives of all 6 trig functions. So I'm going to go ahead and erase, and while I'm doing that, make sure you have everything you need for your notes. And I'm going to go to the next slide, which for you guys is the next page of your notes. So go ahead and turn.
Okay, so now that we went ahead and derived the formula for the derivative of the sine of x, we can see that here are the answers that I would have gotten if I had done that to all 6 of the trig functions. So let's first start with the one we just did. The derivative of sine is the cosine. Repeat the process using the limit definition of the derivative on cosine, and you'll get negative sine. The derivative of tangent will be secant squared. The derivative of cosecant will be negative cosecant cotangent. The derivative of secant will be secant times tangent, and the derivative of cotangent is negative cosecant. Please make sure you make a note card for each and every one of these 6 formulas. You will need to know them by heart. And what I'd like to show you now is how we can go ahead and apply these 6 formulas to derivative problems like the ones below here. I'm again in a few seconds going to fade out to show you how to do these examples on the board, but just remember, all the same rules that we used for the first section on derivatives, like the power rule, product rule, and quotient rule, those all still apply. Even the chain rule. We'll work with the chain rule and derivatives for trig functions in the next section again. So go ahead, make sure you have something good to write with, get ready to do those examples, and once I fade out, I'll be back with those examples on the board.
So in example 1, they give you the function sine of x over 1 plus the cosine of x. And they ask for the derivative, they ask for y prime. So in this particular problem, I have a quotient. So if they ask for y prime and I have something divided by something else, I'm going to go ahead and need to use the quotient rule. So don't forget that that's the bottom function, 1 plus cosine of x, times the derivative of the top function. And now the top function is a trig function. It's something we're going to have to take the derivative of that is now on that table right above the example. And the derivative of sine is the cosine. You just apply a new formula wherever you need it. Quotient rule follows with a minus, the top function, times the derivative of the bottom function. Take it one piece at a time. Derivative of 1 is 0. You don't have to write that. Derivative of cosine is right off of your chart, right above the example. It's negative sine. All over the bottom squared. And now this is the calculus. The calculus is finished. The hard part for you guys is going to be working to the back of the book. You're going to have to know all of your rules from pre-calc in order to do that. So here's some things I see, some things for you to look for, put in your toolkit. I'm going to distribute this cosine. Cosine of x plus cosine squared of x. Don't forget with trig functions, I can write the squared here or put it as a quantity squared. Negative times a negative is a positive sine squared of x. And as soon as you see squared trig functions, you need to start thinking of the Pythagorean identities. Sine squared plus cosine squared is 1. So on the top, this quantity right here can get reduced to a 1. The bottom, don't FOIL out the squaring. Don't go ahead and distribute that, FOIL that, anything. Leave it, because watch what happens. On the top, I get the cosine of x plus 1. And cosine of x plus 1 is the same as 1 plus cosine of x. That's allowed. So if I have one of them on top and two of them on the bottom, this whole thing is going to end up canceling with one of those for a final solution of 1 over 1 plus the cosine of x. And so as you're working on these problems in order to get to the back of the book solution, look for things like that. Look for trig identities, especially Pythagorean identities, to replace. Let's do another example. Again, remember all the same rules that we've already done for derivatives apply. So in the next example, they start us with secant of x, tangent of x. Now secant of x, tangent of x are two trig functions multiplied together. So you have to apply the product rule to them. So in this case, I believe the function started off as g of x. So they want g prime. So for the product rule, remember it's the first function times the derivative of the second. Now you need to know the derivative of tangent, read it off the chart, is secant squared. Plus the second function, tangent, times the derivative of the first function. And the derivative of secant is secant tangent. At this point, the calculus is over. Like I said earlier, when the calculus is done, but you have to work to the back of the book answer. Here's some things they might do. Notice there's a secant here and here. So they may factor that out as a GCF. In this section, you'll see GCFs a lot. You'll be left with a secant squared plus tangent times tangent is left. Tangent squared. And at this point, that's where I think they leave the answer in the back of the book. They might try to change one of these with the Pythagorean identity. 1 plus tangent squared is secant squared. They may subtract a 1 on both sides and replace that so the answer has all secants. Be aware of that. Again, as soon as you see squared trig functions, think of Pythagorean identities. So let's go on to another example, and I want to show you a trick in this one. You'll notice in your notes it says that sometimes it is easier to use pre-calc first. So they start us with the secant of theta times the cotangent of theta. And remember, theta and x, same thing. You're going to have to work with whatever letters they give you. And in this case, I know that secant and cotangent have something in common. I know the secant is 1 over the cosine. And I know cotangent is cosine over sine. And since I knew that those cosines were in common and these are multiplied, I can cancel them and reduce this before doing calculus into 1 over sine, which is cosecant. And then that means if I do pre-calc first, all I have to take the derivative of is this one, as opposed to having to do the product rule like I did in the last one. If you want to go ahead and work out some pre-calc on this one, you can, but it's not going to help you. It'll still make it messier. This one made it a lot easier. So now to take the derivative, they asked for dy d theta. All you need to do is take the derivative of cosecant, which is negative cosecant cotangent. Cosecant theta, cotangent theta. And it was a derivative in one step. So that's why you're really going to make sure that you go back and look at those pre-calc identities, right? Okay. So those were all of the problems where I just was applying the formula. But remember, everything we did with derivatives up to this point is still going to hold. So you're going to need to apply these definitions to problems where you're going ahead and finding slopes of tangent lines, equations.
Okay, so now in examples 4 and 5, we're going to go ahead and find the slope of a tangent line, and we're going to find where the tangent line is horizontal. Then we're going to find the equation of a tangent line and the equation of the normal line. So again, when I fade out, I'm going to be doing these examples on the board. So get ready to work on these.
So if our function is y equals the sine of x, and they give you the x coordinate is pi over 3, when they ask you to find the slope of the tangent line, that's in disguise, then ask you to find y prime, and then plug in the pi over 3. So all you have to do is use your formula for the derivative of sine, which is cosine. And now, you're going to plug in pi over 3 for the x. So my answer will be the cosine of pi over 3. And I actually expect you to know what that is. You took a quiz on the unit circle the first day of school, so you should know what the cosine of pi over 3 is. Now, I don't have the entire circle memorized. I memorized one thing. I memorized that right here is pi over 6, and that pi over 6 has a sine of 1/2. And don't forget, there's a pattern. It goes 1, 2, 3, 1, 2, 3 for all the numerators. Each of these is divided by 2. And then you square root all the numbers. You do not have to write the square root of 1 because it is 1. And then pi over 6, pi over 4, and pi over 3 are the angles from this initial axes right here. So now in order to find the cosine, I know that the cosine is the x coordinate. So the cosine of pi over 3 is just 1/2. And that's your solution. Now on the AP exam, you can, in a problem that's free response, leave your answer as the cosine of pi over 3. But a problem like this is typically a multiple choice, and they reduce their answers. That's why you need to have your unit circle memorized. Now in part B, they want to know for what x values is the tangent line horizontal. And we've talked about that before. Tangent lines are horizontal when the derivative equals 0. And you'll have to solve for x. So I want to know where the cosine is equivalent to 0. Now I want all of the solutions. Now you could memorize the solutions where the cosine is 0 from your unit circle, or you could do what I do. I memorize the graph of cosine, and I know right here and right here are labeled pi over 2 and 3 pi over 2. This will go on forever and ever. So I know to get from pi over 2 to 3 pi over 2 is a distance of pi. So to write my solution, I'll have x equals the first one I come to, pi over 2, and then to get to the next answer, I just have to go another distance of pi, and I will continue that forever, so I can write it as plus pi n. This will take care of all of the values where the cosine is 0, and thereby all of the places where the tangent lines of sine x are horizontal. Now remember I said we're not going to just talk about slopes of tangent lines and all of this stuff where they're horizontal in the slope. You're going to have to also find the equations of tangent lines, and we're going to talk about something called the normal line in the next problem. In example 5, it asks you to find the equation of the tangent line and the normal line, and the graph we're going to work with is y equals the tangent of x. They do give you an x coordinate here. It's in the form of a point, pi over 4, comma 1. Don't forget where that 1 came from. That 1 came from plugging pi over 4 in for the tangent. You should know that the tangent of pi over 4 is 1. If you didn't, you can go ahead and calculate it, or use your fancy little circle right here. Know that tangent is sine over cosine. Radical 2 over 2 divided by radical 2 over 2 is 1. Now, to find a tangent line and a normal line, you need a point and a slope. The point's given. In order to find the slope, we need the derivative. So the derivative is y prime. The derivative of tangent, you can look up on your note card or on your chart, is secant squared. Now we'll have to do that when x equals pi over 4. So in order to do that, you'll need to go ahead and find the secant squared of pi over 4. Remember a few minutes ago I talked about this squared and how you can write the squared here or on the outside of the function squared. I don't know the values for secant. I don't expect you to either, but you should know sine, cosine, and tangent. And you can get everything off of this right here. So I'm going to turn secant into its definition, which is 1 over cosine, but I'm going to write the squared on the outside. So again, I turned secant into 1 over cosine, and I carried the squared through to the outside of parentheses. And now the cosine of pi over 4, well, that's just right here on my chart. Cosine of pi over 4 is radical 2 over 2. So I'm going to evaluate this as 1 over radical 2 over 2 squared. Squaring both the top and the bottom of that bottom there, I'm going to get 2 over 4. This reduces to 1 over 1/2, which is 2. So to find the equation of the tangent line, my point is pi over 4 comma 1, and my slope is 2. Now I can plug right into point slope. So y minus 1 equals 2 times x minus pi over 4. And yes, you can leave that like that. If you want to distribute the 2 through, you can do that. You can move the 1 over if you'd like. You don't have to simplify it any further or get decimals. Now I ask you for the equation of the normal line. The normal line is perpendicular to the tangent line. So you still need a point, which we're going to have as pi over 4 comma 1. But the slope now is the perpendicular slope to the tangent. If I have 1/2, that's going to mean I need opposite reciprocal. Excuse me, I had 2. That means I'll change it to negative 1/2. So again, the slope of the tangent line was 2. My opposite reciprocal slope is negative 1/2. And then all you do is plug into the same equation. Y minus the y coordinate equals the slope, x minus the x coordinate. And at that point, you can stop or work to the back of the book. So don't forget, all of the same rules for derivatives apply in this section. You can go ahead and use your power rule, product rule, quotient rule, and chain rule if you need them. And all you're adding in are the 6 new trig function derivatives.